The second question is, find the set of values of k for which the line y equals to 2x minus k meets the curve y equals to x squared plus kx minus 2 at two distinct points. So you see that the question asking you to get the possible values of k. So you see that k is appeared at here in this equation and again appears at here in the second equation. The first equation is the equation of a line, and the second one is a quadratic equation, which is the equation for a curve. If we want to represent this curve first, it's a quadratic curve. That means it's concave up curve, because when you look at the leading coefficient, it's 1, which is above 0. Therefore, it should be a concave up shape. And the line, we know that it's a straight line. But as long as there are two distinct points of intersection between the curve and the line, therefore we can say that this represents the line. If this is the line, you see that there can be two intersection points. Therefore, we need to consider these two intersection points in order to find the set of values for k. If you remember, in the beginning of first chapter, we said that if there are two solutions in the quadratics, that means the discriminant term of the quadratic formula must be positive. So simply b squared minus 4ac must be above 0 in order to have two solutions. Therefore, we apply this condition to find the possible values for k. But how to apply this? Before the application of this condition, we need to first generate the quadratic equation that involves both of the equations, the linear equation and the quadratic equation. In order to combine both of them, what we can say, we can look at the 2 points and we can say that the 2 points, they have similar x coordinates and y coordinates, which indicates that they share similar y value and x values at the two intersection points. So it means that it's possible for us, when we start to solve the question, we can say that both of the y coordinates are similar. It means 2x minus k equals to x squared plus kx minus 2 at the two intersection points. Then we are going to simplify this equation in order to get the final quadratic equation. After getting the final quadratic equation, then we are applying the condition that we have talked about before. Okay, let's do the simplification. We can send all the terms to the left side. X squared plus kx minus 2. Then you can bring 2x to the right side, becomes negative 2x. Then negative k becomes positive k equals to 0. On the left side, you see that if we simplify this, we get a quadratic equation. Okay, therefore, the next step is to simplify this quadratic equation. You can say it's x squared, then kx with minus 2x. We can take out x as a common factor. Then for this term, k will be left, and for here, only negative 2 is left. Then we have minus 2 with k. You can say it's k minus 2 equals to 0. So this is the final form of the quadratic equation. You can say that the leading coefficient here, a, is 1, and b represents k minus 2, and c is k minus 2. Therefore, when we apply this condition, we have all the required information, a, b, c values. So we can say b squared minus 4ac must be above 0. b is k minus 2, then all squared, minus 4 times ac. a is just 1, then times c is k minus 2, should be above 0. Then we can simplify this, open the bracket, becomes k squared, then 2 times k is 2k times negative 2, it becomes negative 4k. negative 2 squared becomes positive 4. Then negative 4 times 1 times k is minus 4k. Then negative 4 times 2 becomes positive 8. Larger than 0. Okay, you can further simplify k squared. Then minus 4k with minus 4k becomes negative 8k. And 4 with 8, it's positive 12, which is larger than 0. Therefore, in order to get the condition, which is having two intersection points, this inequality must be satisfied. K squared minus 8k plus 12 must be above 0. It should be positive. Then where this curve becomes positive, we can look at the equation on the left side. You see that it's a quadratic equation with a positive leading coefficient. I mean the quadratic equation in terms of k, not in terms of x. It's like we have a new quadratic equation. Therefore, the leading coefficient at here is 1. As long as the leading coefficient is 1 and is positive, therefore, if you want to sketch this equation, you can say that the curve looks like this. So it's concave up. The leading coefficient is positive. Then how about the roots? How about the x-intercept of this curve with the x-axis, which gives us the values for the k? We say this is the x-intercept, and there can be two x-intercepts, which gives us the k values. So k takes two values. How to get that? We can factorize this quadratic equation on the left side. You can say it's k by k. Then positive times negative is negative. Negative times positive is negative. So we have 12. 12, we can say, when we factorize 12, we can say it's 2 times 6. 2 by 6. Because negative 6k with negative 2k is negative 8k, which is the middle term. When we get the middle term, the factorization process is correct. Now, we understood that the two critical points are 6 and 2. So that's why this k value at here represents the first critical point. You can say it's 2, and the second one is 6. Or you can say there are two roots for the quadratic equation on the left, which are 2 and 6. Then, at which position or where the function becomes positive? It's above 0. You see that if the value of k is to the right side, that means larger than 6 and then moving to the right side, the curve is positive. You see, the curve is positive. And also below 2, moving to the left side, the curve is also positive. So therefore, we can say that the solutions or the set of k values are within this range, starting from negative infinity until 2, or starting from 6 then to positive infinity. Therefore, the set of values of k is k equals to, open the set, k is element in the real numbers such that k is less than 2 or k is larger than 6, and then close the set.